lesson on non-standard, delta G, and equilibrium. Non-standard, delta G, and equilibrium. Equilibrium position represents the lowest free energy available. So equilibrium is where the lowest delta G is available. There are other variations, variables to consider, among them pressure and concentration. As pressure and concentration changes, so does the free energy location is. And combine these for the equation derivation, which I'm not going to go into. It's in the book. Delta G for non-standard conditions is equal to delta G naught, which is standard conditions, plus RT natural log of Q. Q, remember, is the product or reactants, the ratios. The standard conditions for delta G is 1 atmosphere, 1 molar, and R, since we're talking about energy, has a value of 8.3145 joules per mole Kelvin. So this is non-standard conditions, whatever the temperature pressure is. These are the standard conditions, and then this is the adjustment factor for that. R is a constant, T the temperature in Kelvin, and Q is the concentration factor, whether it's not over another. Now this equation here, this adjustment factor, tells you whether some reaction goes to completion or not. If your reactants are here and your products are here, if it declines, fairly straightforward, the reaction is going to go to completion, like wood burning. If your reactants are here and your products are here, but your curve has a minimum in between here, this is your equilibrium location here, and it depends upon the variables that you have located there. At equilibrium, speaking about equilibrium, at our equilibrium point here, G is equal to 0 and Q is equal to K. So plugging those into our original equation up here, 0 equals delta G naught plus RT natural log of K. Doing a little manipulation of the equation, a positive delta G naught equals a negative RT natural log of K, the equilibrium constant. And going back to our original from the other day, delta G naught equals delta H naught minus T delta S naught. We can replace the delta G with this. Negative RT natural log of K equals delta H minus T delta S. Divide everything in sight by negative RT. And you get natural log of equilibrium constant is equal to negative delta H naught over RT plus delta S naught over R. But temperature is everything else is pretty much constant. Delta H naught, delta S naught doesn't change for a reaction itself. R's are a constant. Equilibrium constant is a constant. You can separate out this T, and you get natural log of K is equal to the negative delta H naught over R 1 over T plus delta S naught over R, which resembles Y equals mx plus b. So if we were to graph this, where our x-axis is the reciprocal of the temperature in Kelvin, and the y-axis is the natural log of K at different temperatures, you'll get a line that looks like this, and that point right there is delta S naught over R, and the slope is negative delta H naught over R. So you can calculate, since R is constant, you can calculate the enthalpy of an equation and the entropy of an equation from that equation. The line that we're going to do is something different than this. It's another form without graphing, because the graphing can be a bit hairy to do. As summary, now none of this is going to be on the exam. None of this is tested. You might need to know this equation right here. But you do need this so you can understand what we're doing for the labs that we're doing in class. But the summary that you do need, if delta G naught is equal to 0, then K must be equal to 1, and you are at equilibrium. If delta G naught is less than 0, or it's negative, K must be greater than 1, and it will shift to the right. And if delta G naught is greater than 0, that means it's positive, K is less than 1, so these are opposite of what you would say. It would shift left. So the delta G and the K are opposites for spontaneity. That ends this lesson on non-standard G and equilibrium.